This is the pre-lecture video for topic 1.3, which is rectilinear motion, which is motion in one direction. We will get to motion in two dimensions a little bit later. So in class, for this topic, these are the topics that we're going to cover. We're going to talk about a coordinate system and what attributes a coordinate system must have. And then we're going to define these quantities: position, which we use an S variable for, velocity is represented by V, and acceleration, which is represented by an A. And then we're also going to talk about relationships between these three quantities: mathematical relationships and graphical relationships that allow us to figure out one if we know another one. In this video, though, we're not going to cover all that. We're going to briefly talk about coordinate system and define position, and then we're going to define two different velocities, an average and an instantaneous velocity, and then we'll do the same with acceleration. We'll talk about average and instantaneous acceleration, and we'll do some examples of how we calculate those. Okay, so before we can define a position, we need a coordinate system so that we can say, what our position is. And so the attributes that a coordinate system must have is that, first off, it needs a reference point. If I'm saying I have a certain position, I have to say that is my position in reference to some other point. And we can say that the 0 point here that I'm circling in red is our reference. And all of our numerical quantities, my position, say, of 2 centimeters, which might be here, is taken in reference to that 0. Also, the way that this coordinate system is written, you can see that the position 1, 2, 3, 4 increases from the left to the right. So what we can say is that S increases in this direction, and so we can say also that that is our positive direction. Usually we draw an arrow pointing in the positive direction. So S increases left to right. Likewise, S decreases right to left. And we also have a scale, so we've got numbers in here, 1, 2, 3, 4, and so that's an indication of the scale. And the units of that scale, in this case, is centimeters. And then we've got the S variable, that's to indicate our position. So that's our coordinate system, and we can use that then to specify exactly where I am. I am at this green spot, so I am 2 centimeters from to the right of the 0 point. Okay, so now that we have a coordinate system and we've defined position, it's someplace, in this case it's just one-dimensional. That's what we're talking about, one-dimensional, someplace along that line. And of course we could also have negative positions, we could have a -1, a -2, and so forth. Okay, so we can define our position somewhere along this line in reference to the 0 point. Now I can define a velocity. In this case, it's going to be an average velocity over a period of time. And so that's an important point. The average velocity is defined over a time period, and we're going to use this AVE subscript to indicate our average velocity. So our average velocity is a change in position divided by the time it took to move that distance, that change in position. So we use delta S, a change in position, to represent that. And delta T, we use that to indicate our elapsed time. And our elapsed time is always going to be positive. This is always going to be a positive quantity, unless you're in a science fiction movie and you can travel back in time. But in the real world, in this class, delta T is going to be positive. Delta S could be positive or negative. If we're at 2 centimeters, we could move to 3, which would be a positive motion. We could move to -1, which would be a negative motion. So delta S can be positive or negative. So our average velocity then is going to be positive or negative depending on the direction of motion. Okay, so that's our definition of average velocity. Now we can do an example and calculate an average velocity. So here I have a plot of position on the vertical axis, so S plotted, and it has units of feet. And then along the horizontal axis we're plotting time, and it has units of minutes. So maybe there was an object that was moving along a line, and I measured the positions, and I recorded the time at which I recorded those positions, and then I can take that data and plot it, and that's what I would get here. I'm going to assume for the purposes of this video that all the data that I show is known to two significant figures. And so I'll report all of my answers also to two significant figures. So in this case, whatever this object is, it starts at about 1 foot in position at 0 time, and it increases over the first 4 minutes to 10 feet, position of 10 feet, and then from 4 to 8 minutes, it reverses its position and comes back to 1 over the final 4 minutes. Right, so that's how I would describe this motion. It's going out to 10 and coming back to 1. And it's not very fast. You know, covering 10 feet or 9 feet in 4 minutes is not very fast. It's much faster, or sorry, it's much slower than we can walk, or that we normally walk or run. So maybe this is Gary the snail. He doesn't move as quickly as you would expect. He's going to crawl or whatever it is he does fairly slowly. So let's assume this is Gary. And let's calculate his average velocity, and in order to do that, we need to define a time period over which we calculate that average velocity. And so let's say we're going to calculate it between 1 and 4 minutes. So the average velocity for Gary here is going to be, as we defined it, delta S over delta T, change in position over the time, elapsed time. And so if we look here, our change in our elapsed time is 3 minutes, so it's from 1 to 4 minutes. And I measured this distance that was covered over those 3 minutes, and it's a positive 5.1 feet. He was moving in the positive direction. So I can use that information to calculate the average velocity as positive 5.1 feet divided by 3.0 minutes. You might notice that I'm carrying my units all through this calculation. And then my answer, when I divide 5.1 by 3 to two significant figures, is 1.7, and then my units work out to feet per minute. And that's a unit that we would expect for velocity, a length per time, feet per minute, miles per hour, meters per second, something like that. Okay, so that is my answer. And if you look at this, this line that shows an elapsed time of 3 minutes, and the green line that shows a distance change in position of positive 5.1 feet, these quantities, in addition to giving us our average velocity, also define the slope of the red line that's drawn here now. So this is the line that connects the points on the curve at the beginning and the ending of our time period. So this average velocity, we could also say, is the slope of that red line that I've drawn there. That slope is 1.7 feet per minute, 5.1 feet divided by 3 minutes. Okay, let's do another example. In this case, we're going to calculate the average velocity between 4 minutes and 8 minutes. In this case, the elapsed time is 4 minutes, and the change in position is negative. It's moving from 10 at the lowest time, the beginning of the time period, down to 1 at the end of the time period. So my change in position is actually negative 9.0 feet, and my elapsed time is 4.0 minutes, and I get an average velocity of negative 2.25 feet per minute, which I'm going to write as negative 2.3 feet per minute, because I said that I'm going to assume that I know my position and my time to two significant figures, so I can only report my answer to two significant figures. So that's the answer. One more example here. In this case, and this is the same exact plot that we had for the last two examples, Gary starts off at, well, we're going to look at his position at 2 minutes and then compare it to his position at 6 minutes. And in this case, the position is the same. So our delta S is 0 between 2 and 6 minutes. My delta T happens to be 4 minutes. And so my average velocity is going to be 0 feet over 4 minutes. And that's 0. So 0 feet per minute. So Gary was moving between 2 and 4. He moved, from a little bit less than 8 up to 10, to a position of 10 feet at 4 minutes, and then back to a little bit less than 8 at 6 minutes. So he did move during that time period, but he was moving, half the time he was moving in a positive direction, the other half he was moving in a negative direction. Those movements canceled out, and so his delta S was 0, and so his average velocity was 0. Okay, so let's look at this in a different way. So this was from our second example. This is the time period that we looked at from 4 to 8 minutes. And we see we can draw in this red line. The slope of that red line then is going to be the average velocity over that time period. And if I start shrinking the time period, what you'll see is that the red line will more closely approximate the shape and slope of the actual data, the blue curve, as our elapsed time period shrinks. All right, so this is shrunk to maybe a couple minutes, 2 minutes from 4 minutes, and this shrinks to about 1 minute. This shrinks to a time period of about ½ a minute, and this time period here shrinks to about a quarter of a minute. And you can see as this time period gets smaller and smaller, the red line then appears to coincide with the blue line. And so what we can say then is as this delta t shrinks, the red line more closely approximates the shape and slope of the blue line. And we can keep going, and we can actually shrink our time period to 0, which would define just a point, and so then we could define a velocity at a single point, and we're going to call that instantaneous velocity. And we're going to use just a v without any subscripts to indicate instantaneous velocity, and we're going to say it's the limit of the average velocity as this time period shrinks to 0, as delta t goes to 0. And so we can write it like this: average velocity is delta s over delta t. And it turns out that this limit is the slope of the position time plot at a single point. If we can draw a tangent to that curve at a single point and measure the slope of that tangent curve, and we'll do an example of this in a little bit, then that is going to give us our instantaneous velocity. You may also recognize this limit here. This is actually a derivative. It's a derivative of s with respect to t. So if you've already had calculus, you've had calculus 1, then you recognize this. If you haven't had calculus 1 yet and you're taking it now, if you haven't had it, then you'll see this very soon, and this will be defined as a derivative of s with respect to t. Okay, so here's a figure from your book that shows a position. They used x for position. We had used s. But they used x, some position plotted versus time t. And at 4 different times here, they have drawn a tangent curve. So this black line here is a tangent line to the red line at time 1. At this point 1, the black line has the same exact slope as the red curve. And that slope then would give us the instantaneous velocity at t1. So these are tangent lines. And these are also drawn in for P2, P3, and P4. So if we measure those slopes at those times, that would give us the instantaneous velocity at those times. Okay, so let's do an example to calculate instantaneous velocity. This is the same exact position curve for Gary that we already looked at. And I'm going to say, well, let's pick a time of 6 minutes and calculate the instantaneous velocity at that time. And so I can draw a tangent curve, and then figure out, say the rise and the run for that curve, and figure out the slope. So my instantaneous velocity then is the slope of this brown curve. It's going to be minus 4.5 feet divided by 2.0 minutes, and that gives us a minus 2.25 feet per minute, which again I'm going to write to just 2 significant figures, minus 2.3 feet per minute. That's my instantaneous velocity at 6 minutes. Okay, now we can also define similar quantities for acceleration. We can define an average acceleration, and again we have this AVE subscript to indicate this is an average acceleration. It's a change in velocity now divided by an elapsed time, delta V over delta T. And we can do an example. So here's some additional data at a separate time. Maybe Gary is, again, walking along a line in one particular direction, and I measured his velocity at different points in time, again, to two significant figures for both velocity and time, and plotted them here on this curve. So you can see he starts off at 0 time at 1 foot per minute, and then he accelerates. His velocity increases. Maybe SpongeBob just walked in the door. He's excited to see him, so he's hurrying as best he can. He's speeding up to go see Bob. Then after about 3 minutes, maybe he gets tired and he starts to slow down, and his velocity then drops after about 3 minutes. Okay, so let's say we wanted to calculate Gary's average acceleration between 1 and 4 minutes. Our average velocity is going to be the change in velocity divided by the change in time. The change in velocity is positive 3.15 feet per minute, and the elapsed time is 3 minutes, and we can calculate this. We can divide that out, and we get an answer of 1.05 feet per minute, and those are the units that we would expect for an acceleration. It's a length per time again. So it could be meters per second, or miles per hour per second, something like that. Also, I'm going to change this answer a little bit because I had said that we were assuming two significant figures, so this answer should really be 1.1 feet per minute to just two significant figures. Okay, so that's calculation of average velocity. It's not all that different than, average acceleration. It's not all that different than the average velocity, but we're taking a change in velocity now and dividing it by a change in time. We can also calculate an instantaneous acceleration, and we're going to do the same thing we did with the instantaneous velocity. We're going to take the limit of the average acceleration as our time period shrinks to 0, and this now is going to, again, be a limit of delta V over delta T, which is going to be a derivative of velocity with respect to time, and we'll talk more about derivatives in class. And this is also going to be the slope of the velocity time curve, or the velocity time plot at a single point. So here's the same data plot that we had from the previous slide, where Gary sped up and then he slowed down. And let's calculate the average, or the instantaneous acceleration at 2.5 minutes. So we can draw in a tangent line, and the slope of that tangent line is going to be our instantaneous acceleration. You can see that our A here for instantaneous acceleration does not have any subscripts, just A. And so we can calculate our slope. It's going to be 4.5 feet per minute, which is positive. Let me put a positive in here, positive 4.5 feet per minute divided by the time period for this tangent line. And so we get an instantaneous acceleration at 2.5 minutes of 1.5 feet per minute, and it's two significant figures. Okay, so to summarize briefly, when we calculated our average quantities, velocity and acceleration, this was defined over a time interval, so we have some beginning and ending time, and we have a change in a quantity divided by that elapsed time, and it's the slope of a line that we draw between those 2 points, either on the position time curve for velocity or the velocity time curve for acceleration. And then when we calculated our instantaneous quantities, either velocity or acceleration, it was defined at one particular time, and at that time we draw a tangent line and to either the ST or the VT curve, and we calculate the slope of that tangent line. And so that's our instantaneous velocity, which we get from the position time curve, or our instantaneous acceleration that we get from the velocity time curve. Okay, so I think we've tired out Gary from all his translating and accelerating. So we're going to stop here, and I will see you in class.